Hi kids, discussion 3.3. We're going to do this one a little bit differently just because we're going to be drawing a lot of pictures. So we can draw Lewis structures for compounds. We have to determine the shape of a molecule from the Lewis structure. All right. So let me go over these directions. We're going to be drawing Lewis structures for molecular compounds. So the first thing is count up the total number of valence electrons for all the elements. We're then going to arrange the atoms spatially with one atom in the center. Usually that is going to be the least electronegative atom. Carbon will always be in the center. And then we're going to take all those atoms and connect the outside atoms to the central atom with single bonds. Now, as we learned in discussion 3.1, all of the bonds between the atoms will consist of two electrons. One electron from one atom, another electron from the other. So for each single bond we count, it's going to consist of two electrons. So then we're going to distribute the rest of the electrons on the outside atoms first, making sure that we have an octet or 8 electrons around every element. Please note, because a full shell for hydrogen is 2 electrons, hydrogen is perfectly happy with 2 electrons, and we're never going to add electrons to hydrogen. So then what we're going to do once we've distributed all of our electrons is check to make sure that everybody has access to their 8. If some elements don't, then the elements that do will share pairs between the two atoms to produce double and in some cases triple bonds. When you're finished, make sure you count up and make sure that you have the right number of electrons. All right, so I don't expect anybody to know how to do this just from looking at these directions. So let's go ahead and work out some examples. All right, so step 1 is to start with carbon dioxide. It says to add up the total number of valence electrons in the atom. So carbon being in group 14 has 4 valence electrons. Oxygen being in group 16 has 6. Since there are 2 oxygens, I have to double that. So that means there's going to be 12 plus 4, 16 total electrons. Now, we mentioned put the least electronegative element in the center. Well, there's an easier way to think about that. We are only going to be dealing with molecules that have one atom in the center. So when you look at the formula, whichever one you have one of, that will usually, well, in this case, and for this class and this lesson, they will always be the one that goes in the center. So I'm going to put carbon in the middle, and I'm going to connect the 2 atoms of oxygen to carbon. Now I have to count the total number of electrons I've already distributed. So I have 16 in total to distribute, and I've put in 2 single bonds for a grand total of 4. Since I have to distribute 16 and I've distributed 4, I have 12 more electrons to distribute. Now let's go ahead and put those on the outside atoms. So 2, 4, 6, 8, 10, 12. At this point, I've distributed all of my electrons. I have 16 total. Let's go ahead and check. 2, 4, 6, 8, 10, 12, 14, 16. So that's good. Now I have to check to make sure every atom has access to 8. So when I look around oxygen, I see 2, 4, 6, 8. Don't forget those 2 electrons in the bond count. And 2, 4, 6, 8. Beautiful. But carbon only has the 2 bonds. Carbon has 4 electrons. So it needs 4 more. So each oxygen atom is going to share a pair of its electrons and make a double bond between itself and carbon. So whenever we do these, you always kind of have like one little mock-up structure. It shows you what you're doing, and then one nice, neat, tidy one. So these 2 lone pairs move in to make double bonds. So we'll have a pair of double bonds between carbon, and there's still 2 pairs of non-bonding electrons on each oxygen atom. This is the Lewis structure for carbon dioxide. We can still check the total number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, and it matches. All right, now let's do the same thing for water. First thing we got to do always is add up the valence electrons. Hydrogen, being in group 1, has 1 valence electron, and there's 2 of them, so I'm going to go ahead and double that. To that, I'm going to add the 6 valence electrons that are in oxygen for a grand total of 8. There's 2 hydrogens and 1 oxygen, so I know that oxygen goes in the middle, and the hydrogens go on the outside. I've distributed two electrons per bond, so 4 electrons total. I need to distribute 8 all day, so I have to distribute 4 more. Again, we never add electrons to hydrogen, so we're going to put those electrons on the oxygen. 2, 4. Double check. You have 2, 4, 6, 8 electrons. Here is the Lewis structure for water. I'm going to go ahead and put a square around our final structures. All right, let's do a couple more examples, and I'll have you guys do a couple for practice. All right, so this is called the carbonate ion. We learned about the carbonate ion in topic 3.2. All right, so let's go ahead and add up all the electrons. Carbon has 4 valence. Oxygen has 6. There's 3 oxygens, so we have to multiply that 6 by 3. And we have this -2 charge. Whenever you see the formula for a polyatomic ion, we have to consider the charge. If CO3 had all the electrons it needed, it would be neutral. However, this -2 charge means it has 2 additional electrons. So we're going to have to add those 2 additional electrons to our count. So it's going to be 18, 20, 24 total electrons. So now we're going to arrange the atoms in space. There's 1 carbon and 3 oxygen. That means carbon goes in the middle. I'm going to move these other pages out the way so they don't get soaked. And I'm going to go ahead and connect the carbon to the 3 oxygens and connect with single bonds. So here I've already distributed 2, 4, 6 electrons. Since I have to distribute 24 total, I have to distribute 18 more to the outside atoms first. So 2, 4, 6, 8, 10, 12, 14, 16, 18. If you want, you can go ahead and count. 18 electrons on the oxygen plus the 6 in the bonds makes 24 total. So now I'm going to check to make sure everybody has an octet. Well, each of the oxygen atoms has 2, 4, 6, 8, 2, 4, 6, 8 electrons around them, but carbon just has the 3 bonds. So one of those, since carbon has the 3 bonds, it's got 6 electrons around it, which means it needs 2 more. So one of those oxygen atoms will share a pair of its electrons to make a double bond. So the final structure we're going to have a double bond between this carbon atom and this oxygen. And there's still 2 lone pairs or non-bonding pairs of electrons on it. So here is our final structure for the carbonate ion. All right, let's just go ahead and do this ion here. You didn't learn about this polyatomic ion, but it's called nitrite. First thing we're going to do is count up the valence electrons. Nitrogen is in group 15, so it has 5. Plus, by now, we all know oxygen has 6, and there's 2 oxygens and a -1 charge. So we're going to add it all together. I get 18 total electrons. There's only 1 nitrogen and 2 oxygens. So that tells me nitrogen goes in the middle, and I'm going to connect to the 2 oxygen atoms. So I've distributed 4 electrons so far. I have to distribute 18 all day, so I have to do 14 more, starting on the outside. 2, 4, 6, 8, 10, 12. Ooh, the central atom gets a pair here too. Now remember, we fill in the outside electrons first, but if there's any left over after all those outside atoms are satisfied, they can go on the central atom. So now I'm going to go ahead and count to make sure that each atom has 8. Well, the oxygens have 2, 4, 6, 8, 2, 4, 6, 8, but nitrogen only has 2, 4, 6. It needs 2 more electrons, so one of those oxygens will share a pair between itself and nitrogen. So the final structure for the nitrite ion will look like this. All right, now I want you guys to practice drawing these structures all on your own. Again, just follow those steps. Feel free to rewind the video and go back to where we started, and that might help you. So go ahead and pause the video, go ahead and draw out these 2 structures, and come back to check your work. Okay, so this is the nitrate ion. First thing I'm going to do is count up the electrons. 5 from nitrogen plus 18 from oxygen. Again, it's 6 but 6 times 3, and the 1 for the -1 charge. So this is going to be 23, 24 electrons total. I put the nitrogen in the middle, and I connect the 3 oxygens to it with single bonds. I've distributed 6 electrons so far, so I have to distribute 18 more. So 2, 4, 6, 8, 10, 12, 14, 16, 18. That's my 24 electrons. All the oxygens are happy with 8, but nitrogen only has 6, so one of those oxygen atoms, it doesn't matter which one, is going to go ahead and share a pair to make a double bond between itself and nitrogen. So the final structure for the nitrate ion, the way I've drawn it here, looks like that. And finally, sulfur trioxide. There are 6 valence electrons in sulfur, plus the 18 from the 3 oxygens. That's going to give us a total, again, of 24 electrons. I bet you can see where this is going. We're going to put the sulfur in the middle, connect the 3 oxygens, single bonds. I have distributed 6 electrons so far, so I have to do 18 more. 2, 4, 6, 8, 10, 12, 14, 16, 18. Sulfur only has 6 electrons around it, so it's going to need a pair from that oxygen. When we draw our new nice neat structure, we'll have 1 double bond between sulfur and oxygen and 2 single bonds. When you redraw your structure, make sure you're drawing it carefully so that you still have the right number of electrons. I should have 24 electrons in here, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Beautiful. All right, so that's drawing the structures. Now, from the drawn structure, you can work out what the shape of the molecule is. We work out the shapes by something called Vesper theory. Vesper stands for valence shell electron pair repulsion. Essentially what this means is that all of the valence electrons in an atom will arrange themselves, so that they are as far apart from each other as possible. Remember, electrons repel, so they're all going to move around that central atom in such a way that they're as far away from their neighbors as they possibly can be. So we're going to be looking at 4 different bonding situations, and these different bonding situations are going to lead to different shapes. The first one is when we have 2 atoms bonded together. The second is when there are 2 atoms with 1 central atom, or 3 atoms bonded together. The third is when we're going to have 3 atoms bonded to a central atom, so I'm just going to put quotes there. And the fourth is when there are 4 atoms bonded to a central atom. Now, each of these different bonding situations is going to give us a different shape. So let's go ahead and look at scenario A. So consider these elements points. The shortest distance between 2 points is a straight line. So whenever you have 2 atoms bonded together, the shape that arises from that situation is called linear, a linear shape, or the atoms are arranged in a line. Scenario B is when we have 3 atoms bonded together, or 2 atoms bonded to a central atom. Now there are 2 possible shapes we can get here. So remember that this carbon atom here in carbon dioxide only has 2 sets of electrons, 2 bonds coming out of it. So there's no place that those bonds could be any further away from each other than on opposite sides of the central atom. So when you have 3 atoms bonded together with no other electrons on the central atom, no lone pairs of electrons, the shape you get is also linear. So we can get a linear shape from 2 scenarios. Scenario A, 2 atoms bonded together, or scenario B, 3 atoms bonded together as long as there are no lone pairs. So what I'm going to do here for this one is flip the camera up in a second, show you my shining face. In water, H2O, there are 3 atoms bonded together. But there are also lone pairs on that central atom. So just imagine for a hot second. Imagine for a hot second like there's only 2 bonds with no electrons. They're not going to be any farther apart from each other than if they're on opposite sides. Not fully in the video, I gotta go this way. On opposite sides of the central atom. However, if I take electrons, I can't stay in the frame. There we go. If I take electrons and add them to the central atom, those electrons are going to push on those bonds, bringing them down into this shape. Now, those electrons up here aren't bonds. They're just lone pairs of electrons, but they still exert a pressure on those bonds, pushing them away. So whenever you have 3 atoms bonded together with lone pairs on the central atom, the shape you get is a shape called bent. And you can clearly see that water looks bent. It's bent because of the 2 lone pairs of electrons. These lone pairs push down on those bonds. So if I put a lone pair up there in carbon dioxide, there isn't, but if I did, then those bonds would be pushed down there in that bent arrangement as well. All right, almost done here. Scenario C is when we have 3 atoms around a central atom. Now again, lone pairs make the difference. So if you have 3 atoms around a central atom with a lone pair or lone pairs on the central atom, then again, this lone pair that we put up here has a force that pushes those bonds down. The shape we get here is called trigonal pyramidal. It's called trigonal pyramidal because if you trace all the bonds, it kind of looks like a pyramid. Trigonal refers to the 3 bonds coming from it. Now, if you have 3 bonds around a central atom with no lone pairs on the central atom, then there's nothing pushing the bonds down, so the way they're going to be as far away from each other as possible is to be in the same plane of space, splitting a circle 3 ways or 120 degrees apart. So if we flip this on its edge, in fact, I don't know why I'm not showing you these molecules. Here's an example of a trigonal planar shape or trigonal planar. If you look edge on, all of those bonds are in the same plane 120 degrees apart. Shucks. All right, so this shape is called trigonal, again, because it's 3 bonds, but instead of being pyramidal, it's trigonal planar because all the bonds are in the same plane. And finally, 4 atoms around the central atom, like this, will always give you the same shape called tetrahedral. Here's a model of a tetrahedral shape. All right, that's it, kids. That's it for discussion 3.3. Make sure you let me know if you have any questions. This is another one of those skill-based practice ones. If you practice drawing the Lewis structures, you'll be fine. If you practice looking at the different scenarios you get in your Lewis structures to determine the shape, you will also be fine. All right, kids, see you in class.